In UPSC Chemistry Optional Paper 2, Organic Chemistry forms the bulk of the syllabus, and reaction mechanisms is its structural backbone. In UPSC, writing a reaction mechanism is not just about showing curved arrows, it requires explaining electronic effects, stereochemistry, and reactive intermediates. 1. Fundamentals, driving forces of mechanisms. Every organic reaction is driven by two key principles. A. Core reactive intermediates. Understanding the stability, geometry, and reactivity of intermediates is essential for UPSC mechanism questions. Intermediate. Structure and hybridization. Stability order, key feature. Carbocation. Trigonal planar, sp squared, 6 valence E caret. 3 caret, circ greater than 2 caret, circ greater than 1 caret, circ. Hyperconjugation and inductive effect. Prone to rearrangements. 1, 2 hydride, alkyl shifts. Carbon or planar, if conjugated. 8 valence E caret. Stabilized by electron withdrawing groups. I, M. Fluorine versus chlorine stability anomalies. CF_3 caret vs CCl_3 caret. Free radical. Planar, shallow pyramid. sp squared. 7 valence E caret. Stabilized by resonance, allylic, benzylic, and hyperconjugation. Carbon. R_2C. Singlet, sp caret 2, paired. Triplet, sp, unpaired. Singlet. Stereospecific addition, concerted. Triplet. Non-stereospecific. Diradical step. Nitrene. Rn. Isoelectronic with carbons. Key intermediate in Hofmann, Curtius, Schmidt, and Lawson rearrangements. 2. Nucleophilic substitution reactions. S_N1 versus S_N2 versus S_Ni mechanisms. S_N2, bimolecular nucleophilic substitution, concerted single step, involves a pentacoordinate transition state. Stereochemistry, 100% Walden inversion. Factor, solved best in polar aprotic solvents, e.g., DMSO, DMF. S_N1, unimolecular nucleophilic substitution, stepwise, formation of carbocation intermediate, rate determining step. Stereochemistry, racemization, often with partial inversion due to ion pairs. Favored by polar protic solvents, H_2O, ETOH, stabilizing carbocations. S_Ni, internal substitution, classic example. Reaction of alcohols with SOCl_2 in non-ether solvents yielding alkyl chlorides with retention of configuration via an ion pair mechanism. 3. Elimination reactions, E1, E2, E1Cb. Elimination competes directly with substitution based on temperature, base strength, and substrate structure. E2 mechanism, concerted antiparaplanar elimination. Requires a specific dihedral angle, 180 carat, circ, between the leaving group and the beta hydrogen. E1Cb, elimination unimolecular conjugate base, occurs when the leaving group is poor, e.g., F, O, and the beta hydrogen is highly acidic due to strong electron withdrawing groups, e.g., CF_3, NO_2, CN. Regioselectivity rules. Saitsev's rule favors the more substituted, thermodynamically stable alkene, standard E1, E2 with unhindered bases. Hoffman's rule favors the less substituted alkene, occurs with bulky bases like T-Bo caret, poor leaving groups like F, or quaternary ammonium salts. 4. Electrophilic and nucleophilic addition reactions. Electrophilic addition to carbon-carbon multiple bonds. Markovnikov's rule and anti-Markovnikov effect. Addition of HX across unsymmetrical alkenes via carbocation versus free radical mechanism. Karish effect via peroxides. Stereospecificity. Bromination. Bridge_2, CCl_4, goes via cyclic bromonium ion leading strictly to anti-addition. Nucleophilic addition to carbonyl groups, C=O, carbonyl carbons are strongly electrophilic. Cram's rule, Falcon-Ann model, used to predict the stereochemical outcome of nucleophilic attack on chiral, alpha-carbon-carbonyl compounds. 5. Electrophilic and nucleophilic aromatic substitution. Electrophilic aromatic substitution, ARS_E, includes nitration, sulfonation, halogenation, and Friedel-Crafts alkylation via Welland intermediate, or rhenium ion. Directing effects. I-M groups are meta-directing and deactivating, except halogens, which are deactivating but ortho-para-directing due to plus M greater than I. Nucleophilic aromatic substitution, ARS_N, requires strong activating groups, e.g., NO_2, at ortho-para positions via Meisenheimer complex, or proceeds via benzene intermediate. Elimination addition mechanism using strong bases like NaNH_2, NH_3. 6. High-yield rearrangement mechanisms in Paper 2. UPSC explicitly asks for step-by-step mechanisms of name rearrangements. Pinnacle-Pinacolone rearrangement. Migration of alkyl-aryl groups to an electron-deficient carbocation center. Migratory aptitude. AR greater than H greater than alkyl. Beckmann rearrangement. Oxine to amide conversion using acid catalysts. H_2 SO_4, PCl_5. Anti-migration of the group relative to the O group is strictly observed. Favorsky rearrangement. Alpha haloketones to esters, carboxylic acids via cyclopropanone intermediate. Claisen and Cope rearrangements. Classic, 3 sigma-tropic shifts proceeding via chair-like transition states. Key tips for scoring high in UPSC Paper 2 mechanisms. Draw clear curved arrows. Always show movement of electron pairs from electron-rich sources, nucleophiles, bonds, to electron-deficient sinks, electrophiles. Label intermediates and rate-determining steps, RDS, clearly mark carbocations, carbonyls, or transition states, D-dagger, and specify the slow, RDS step. Address stereochemistry. Specify whether a reaction is stereospecific, e.g., E2, S_N2, hydroboration oxidation, or stereoselective. Incorporate isotopic labeling and kinetic evidence. Mention isotope effects, e.g., K_H, K_D for primary kinetic isotope effects in E2, when justifying a proposed mechanism. Where would you like to focus next for your Paper 2 preparation? Solve a previous year UPSC mechanism question. Review pericyclic reactions and frontier molecular